Bismillah ar-Rahman ar-Rahim. This is lecture 13 on positive definite matrices. These are symmetric matrices with positive eigenvalues. The eigenvalues of A equal to A transpose are positive if and only if the pivots are positive. An important case is the 2 by 2. So when does A, which is A, B, B, C, have lambda 1 greater than 0 and lambda 2 greater than 0? Remember that lambda 1, lambda 2, the product of eigenvalues is equal to the determinant. So the determinant must be positive. And lambda 1 and lambda 2 should both be positive. Also, t equal to lambda 1 plus lambda 2, which is the trace, it's equal to A plus C. That requires A greater than 0 and C greater than 0. Another test for positive definiteness is that the pivots must be positive because lambda 1, lambda 2 equals the product of the pivots. Okay, and for the 2 by 2 matrix here, the pivots are A, should be greater than 0, and the determinant AC minus B squared over A greater than 0. Positive definite quadratic forms. If we take the product X transpose A times X, okay, this should be greater than 0 if A is positive definite for any non-zero vector X. So if we take the product, X transpose is the row vector XY times the matrix A multiplied by the column vector XY. It is AX squared plus 2BXY plus CY squared. This should be greater than 0, except when X equals 0 and Y equal to 0. So the function f of X and Y is a quadratic function, AX squared plus 2BXY plus CY squared, okay, is a function of the second degree. It is a nonlinear function. It's nonlinear in X and Y. The second derivative of f of X with respect to X and Y, fxx, fxy, fyy are all constant. So if we take the first derivatives, we'll see that df dx gives us an equation which is 2ax plus 2by. It's linear in X and Y. And df dy is also linear in X and Y. It gives us 2bx plus 2cy. Okay. And the second derivative can be arranged in a matrix. Okay, it is 2a, 2b, 2b, 2c, which is 2 times the matrix A. Okay. So where does calculus use second derivatives? They give us the bending of the graph of f of X and Y. When f double prime is positive, the curve bends up from the tangent line, indicating a point of minimum when x equals 0, y equals 0. So the curve of y equal to ax squared, for example, is a parabola. If a is greater than 0, the curve is convex up, so we have a minimum point at x equals 0. And that requires a to be positive, greater than 0. And it is a maximum if a is less than 0. For the two variable function f of X and Y, the matrix of second derivatives determines whether f, which is X transpose A times X, has a minimum or a maximum or a saddle point. It has a minimum at xy both 0 if and only if A is positive definite. So we take an example. The matrix A is symmetric, 1, 2, 2, 7. And by Gaussian elimination, we have U, which has the pivots 1 and 3. on the diagonal. Okay, so if we expand x transpose ax here, we get x squared plus 4xy plus 7y squared. It is positive because it is the sum of squares. To see that it is the sum of squares, we complete the square for x. For the first two terms, if you expand x plus 2y squared, it gives these two plus another term which is 4y squared. So we subtract 4y squared from 7y squared, becomes 3y squared. So we see that f is now a sum of two squares, which is positive. And the multipliers here are the pivots, 1 times the first term in x and 3 times y squared. This is the second pivot. Okay. Notice also that the term inside the bracket here, inside the square, the 2 is the multiplier in Gaussian elimination, L21. I have a proof for any 2 by 2 positive definite matrix. When A is positive definite, f of xy can be written as a sum of squares. So for the general matrix A, which is A, B, B, C, f of x and y is x transpose A times x. It is ax squared plus 2bxy plus cy squared. We complete the square for x. Okay, we take A common, so it becomes x plus b over ay squared. So we have to subtract b squared over a. So it is c minus b squared over a, which simplifies to ac minus b squared, which is the determinant divided by a times y squared. So it is again the sum of squares, and each term is multiplied by the pivot. The first pivot is a, the second pivot is the determinant divided by a. So using Gaussian elimination on A, the pivots are obtained, and we can write A in the form LDL transpose. This is the LDL transpose factorization of A. Okay, so this is A equal to L times the diagonal matrix having the pivots and times L transpose. So every positive definite symmetric matrix factors into LD L transpose with positive pivots.